Before watching this video, please subscribe this channel and click on bell icon to get the notifications for the upcoming classes.
In this session, I want to explain the Bell-Coleman cycle, air refrigeration. So, Bell-Coleman cycle, Bell-Coleman cycle. So this Bell-Coleman cycle is also called as a reverse Brayton cycle. So, also called as a Joule cycle also. So, air is used as a refrigerant here. So, Bell-Coleman cycle, the basic line diagram for Bell-Coleman cycle is, this is the refrigerator, this is the compressor. The main elements of the Bell-Coleman cycle is the compressor, cooler, expander and refrigerator. So here the air enters from the refrigerator by absorbing heat. Here the products to be cooled are placed in this place that is called as the refrigerator. So this is the actual refrigerator. So the products are placed here to cool. So the air from this refrigerator, which is in the condition of warm condition, as it is absorbs the heat here. So this warm air coming to the compressor where it is compressed adiabatically. That is, in the compressor the warm air compressed adiabatically. So to high pressure, that is, its pressure is increases. As the pressure increases, its volume, its temperature also increases and its volume is decreases. So here from high pressure, high temperature, air enters to the cooler. Here in this cooler at constant pressure, as here in the compressor, as the pressure increased and temperature also increased, here in the cooler at constant pressure, by maintaining the constant pressure, the high temperature air is cooled to lower temperatures. So here that's why cooling process, that is, heat is removed from the air, high pressure air. So during this cooling, pressure remains constant and the temperature is going to be reduced by using normal air. So the temperature of the air is reduced at a constant pressure process. In this process, the constant process, heat is removed at a high temperature. So the heat is removed at high temperature. As the air coming from compressor at high temperature, here heat rejected at a high temperature. So from this the condition of air just coming out from the cooler is high pressure, low temperature air. This high pressure, low temperature air is expanded here. This is the expander. As the expansion means, that is, the pressure of the air is decreased. As the pressure of the air is decreased, automatically its temperature once again falls to lower temperatures. As the high pressure air expands, as the high pressure air expands, its temperature drastically reduced with the reduction of temperature. That is the chilled air. The chilled air from the expander so enters into the refrigerating space where the products are to be cooled are placed. Here the chilled air absorbs the heat from the products placed here. So then the chilled air got warm up. So then the cycle repeats. The warm air enters to the compressor. So this can be written in the, this can be represented in PV diagram and TS diagram. So in the PV diagram, this is the process. This is the compression process. So here 1 to 2 in the compressor. So this is the process. So you should note that the cycle starts here, not here. In normal cycles, all the cycles are started here, but in Brayton cycle, this cycle starts from this place. That is in this the compressor, that the air enters in the compressor. at a low pressure, so its pressure is drastically increases in compressor. So this is the adiabatic process. This process is indicated in a TS diagram as a straight line, here 1 to 2 as a straight line. So as the adiabatic process, entropy is constant, that's why this is the straight line. Here as the compressor, temperature is increases from T1 to T2. This is the highest temperature in the Bell-Coleman cycle. As the temperature increases, so then it is moves to the cooler, here heat is rejected. This is the constant pressure process, so it is represented here in constant pressure process. After that it is expanded, the pressure is drastically reduced from P3 to P1 and P3 to P4. Here the temperature once again falls. Here during the cooling, temperature is reduced. Here temperature drastically falling. So here temperature is fall, and at the same time, now this is the here 4 to 1 is the adiabatic constant. This is the adiabatic process. Here 4 to 1 adiabatic expansion. Here 4 to 1 is the constant pressure heat addition. That is the heat added during the refrigerator. Here heat is rejected to surroundings. Here heat is absorbed from the refrigerator, that the products to be cooled. So you can directly, that is 1 to 2 is the adiabatic compression in the compressor. So 2 to 3, that is the constant pressure heat rejection. As the constant pressure heat, the formula for heat rejection is equal to Cp. That is the, so 2 to 3 process is the constant volume. The area under the TS diagram is called as a heat transfer. The area under the 2-3 is called as the heat rejected, that is Cp into T2 minus T3, that is high temperature minus low temperature. So Q rejected is Cp into T2 minus T3. This is the heat rejected at high temperature. So next one is the 3 to 4 adiabatic expansion in the expander. So here temperature is drastically falls. So 4 to 1 constant pressure process. So here heat is absorbed from the refrigerants, absorbed from the products to be cooled. So that is heat absorbed. Once again, as the heat absorbed, the temperature is raised, that is warm up to the chilled air. So 4 to 1 the temperature, as the heat absorbed at constant process, the heat absorbed is equal to Cp into T1 high temperature minus high temperature minus low temperature. So that is T1 minus T4. So here you can take this as a, so here 4 to 1 is the constant pressure heat addition. That is the, here heat addition means the heat is added in the from the products to be cooled. As the heat added means the products are going to be cooled. That is the refrigeration effect. That is called as a N. Then N is equal to heat added is equal to Cp T1 minus T4. This is the actual refrigeration effect. So now we are moving to the COP. So COP is the, as it is already explained you in the previous video, that is the COP is the ratio of refrigerating effect produced, that is N by W. So N by W. So as the W is equal to normal formula heat rejected minus heat added. Heat rejected means the heat added. That is the N by W. N is equal to heat added by heat rejected minus heat added, that is the N by W. Here we already written the formula. Q is equal to heat rejected is Cp T2 minus T3 during the 2-3 process at a constant volume, constant pressure process, and 4 to 1 heat rejected. So then you can submit this heat Cp T1 minus T4 by, so heat rejected, that is Cp T2 minus T3 minus Q added, that is Cp T1 minus T4. This is the, so by submitting this only heat rejected and heat added, by submitting, as the Cp is common both on so top and bottom, the Cp can be directly removed, that is T1 minus T4 by T2 by T3 minus T2 minus T3 minus T1 minus T4. This is the COP of the refrigerator. So this formula can be reduced by considering the polytrophic process or the adiabatic process, that is a process 1 to 2. So that is 1 2 and the relation adiabatic relation. So this is the adiabatic relation, the relation between the 1 to 2. T2 by T1 is equal to P2 by P1. So T2 by T1 is equal to P2 by P1 whole to the power of gamma minus 1 by gamma. If the P2 by P1 is taken as it is the compression ratio RC, as the here the pressures are same, P2 and P3 same, and P4 and P1 and P4 is same. That is compression ratios, and this is the compression, this is the expansion, both are same. Then this can be taken as a for 1 to 2 process and 3 to 4. T2 by T1 is equal to P2 by P1 whole to the power of gamma minus 1 by gamma. T3 by T4 is equal to P3 by P4, that is gamma minus 1 by gamma, is equal to here RC, that is the compression ratio, this is the expansion ratio. As the P2 is equal to P3, P1 is equal to P4, both are equivalent. As T2 by T1 is equal to R to the power of gamma minus 1, as T3 by T4 is equal to R to the power of gamma minus 1 by gamma, then both are equal, that is T2 by T1 is equal to T3 by T4. Then you can take this T2 is equal to, so T1 into T3 by T4. So once you get the relation, you simply submit the values here, that is the COP is T1 minus T4, which is already derived here, the T1 minus T4 by T2 minus T3 and minus T1 minus T4. Just placing the value of T2 here, that is T2 here, all are same, so T1 minus T4, and but only exchanging the value of T2, that is T2 is equal to T1 into T3 by T4 minus T3, so T1 minus T4 by taking this value as a common, that is T3 by T4, so outside, so T3 by T4, once T3 by T4 is coming out, this is the T1, so T3 by T4 into T3 is equal to T4, then T1 minus T4, T1 minus T4, all are common. So once you take the common as a, so you can get the T3 minus T4 minus 1. This is T4 and T4, T1 minus T4 both are cancelled here, that is T3 minus T4 by minus 1 here. So then you can take this as a 1 minus T3 by T4 minus 1. So T3 by T4 also, here there is a T3 by T4 is equal to T2 by T1. So that is 1 by T2 by T1 minus 1. So you can LCM, that is T2 minus T1 by T1. Then this moves outside, that is T1 by T2 minus T1. This is the COP of the Bell-Coleman cycle. Bell-Coleman cycle COP is equal to T1 by T2 minus T1. You can take T1 is the temperature at which air enters into the compressor. T2 is the temperature at which air leaves the compressor. The initial temperature before entering the compressor, after compressor. So this can be rewritten as T2 by T1 is there is a relation, that is RC to the power of gamma by T2 by T1 is equal to RC by RC compression R to the power of gamma minus 1 by. You can also written this as a 1 by R to the power of gamma minus 1. Gamma minus 1 by gamma minus 1. So then the COP of the Bell-Coleman cycle can be written as, so T1 by T2, T1 by T2 minus T1, or 1 by R to the power of gamma minus 1 by gamma minus 1. Sometimes these compression ratios may be changed. Okay, this is the COP of the Bell-Coleman cycle.
Thank you for watching this video. Please subscribe this channel and click on bell icon to get the notifications for the upcoming classes, and share